So let's look at another example of a proof by contradiction for an implication statement. And actually, this is going to be a biconditional statement. We want to prove that for every x not p of x, if and only if there does not exist an x such that p of x. And notice here, this is actually showing one of the things that we've seen before, one of our laws about how to work with quantifiers and our logical operators. This is showing that these two statements here are logically equivalent. So let's go ahead and show how we can prove that this and this are logically equivalent, because that's what the biconditional means, using a proof by contradiction. So again, this is a biconditional statement. So I'm going to have to split it into two different parts. So I'm going to indicate that my first part, I'm going to be looking at the forward direction just by writing this. So my very first step is I'm going to look at the forward direction. So what I want to show is for every x not p of x implies not there exists an x such that p of x. So I want to show that this is true, and I see this is an implication statement, and that's a p, and that's my q. That's my hypothesis, that is my conclusion. So I want to use a proof by contradiction here. So I declare in search of a contradiction, I'm going to be using a proof by contradiction, I need to assume something. And oh bummer, I'm in the middle of an exam and I've forgotten for a proof by contradiction of an implication, what do you assume? Do you assume P and not Q, or Q and not P, or was it an or an and, or how did that work? Well, we can quickly rederive that, because we remember that our basic proof by contradiction is assume your statement is false and then derive a contradiction, and therefore you can conclude your original statement. So here our statement is a P implies Q. So we had a P implies Q, and our basic proof by contradiction says that we need to assume not this thing. So we can quickly rederive what we need to assume by noting that this is logically equivalent to not P or Q, and applying our laws, we get this as P and not Q. Okay, there we go. So now I've remembered that for a proof by contradiction of this implication statement, I need to assume P, that statement, and not Q. So assume P, that is for every x not P of x, and not Q, this whole expression. Well, take a look at this. I have a double negation. So this double negation right here says this negation and that negation, they cancel each other out. And so this is logically equivalent to there exists an x such that P of x. Oh wait, there exists an x such that P of x, and for all x's not P of x, that's a contradiction. So that's my contradiction, because here it says there's some value such that P of x is true, and this says for all values P of x is not true. Those both can't coexist, therefore it's a contradiction, and I've finished with my forward direction. So let's go ahead and do the same thing for the reverse direction. So for this by implication, I'm going to consider now the other direction. So I indicate that again by using this little arrow here. And so now what I want to show is the right-hand side implies the left-hand side. So this is what I want to show. And again, this is an implication statement. So I identify that this first part is my hypothesis. The second part is my conclusion. And so if I want to argue by contradiction, I would then assume P and not Q. In search of a contradiction, assume P, assume that's true, and not this. So, I've assumed both of these are true, and let's take this one. So if I take this one, I notice that I can simplify this. I can simplify this because I already know how my quantifiers and my logical operators interact with each other. So this right here is actually using the fact that I know how this universal quantifier and this negation statement here work. I already know, because I've previously shown using truth tables and other arguments, that I know that this statement, I know how to distribute this not into the universal quantifier. That means I need to flip that to an existential one and then negate what's on the inside. Not P of X, but that's a double negation. So this is logically equivalent to there exists an X such that P of X. Well, have we derived a contradiction? Yes, in fact, we have, because I see here it says there exists an X such that P of X, but we've assumed not there exists an X such that P of X. So indeed, this statement and this statement cannot coexist together. This is a contradiction. And so, since I've been able to show both my forward direction and my reverse direction, both by using a proof by contradiction, I can therefore conclude that my original statement is true. And I am finished.